Welcome back, grade 11s. This is the continuation of electrostatics, but then now we'll be talking about electric fields. And then let me remind you of the work we did in grade 10, whereby now we are having a charged object. Suppose it is a charged object, but then now we don't know what type of a charge is it, whether it's a positive charge or a negative charge. Let us say we do not know. Then now what we use, we must use a positive charge. Usually to test for the nature of the charge, we use a positive charge. Small charge is called a test charge. Now with a test charge, what you do, you just place a test charge right here, close to that charge. And then what is going to happen? You are going to see that if this positive charge, you know this is a positive charge, if it moves away, which means it tells you that this charge is positive. Why? Because now the like charges repel. Then now if you place the very same charge next to another charge and then it moves towards that charge, what does it mean? Simply means now the charge is negative. Why? Because the unlike charge attract. You know, this is it. And then now, but then now, interesting enough, we don't have to place it in contact with this one. It must be at a certain distance from that one, and then it experiences a force. Even though we placed it somewhere here, it is still experiencing a force, which means there is a field, there is a region around this charge at which any point charge or any charge is going to experience a force. That region, therefore, is called what? The electric field. Then, if you check here, suppose we have two scenarios here, scenario A and scenario B. With scenario A, we have the positive charge. We know now it is a positive charge. Then we have our test charge. Then we place it at distance r. And then now this point charge is going to experience a force F1, which is the electrostatic force. We know that one according to Coulomb's law. But suppose now we do the very same thing. We place this now. But now we increase the what? The distance. You are going to see now this charge is going to experience F2. But now this F2, interesting enough, this F2 now is going to be weaker than F1. But as you can see, it is going to be a quarter of F1. This is according to Coulomb's law. Now, Coulomb's law says that the force or electrostatic force is inversely proportional to the square of the distance. So if we are increasing the distance, therefore this is also. We know that a force is a push, or a force is a pull, which means a force has to do with how strong you are pulling it. Yes. If you are pulling it much stronger, then now we are saying the force is going to be bigger. You applied more force. Then this leads us to something now. Suppose now you have this charge here, and then you place this point charge here. And then you realize that this charge moves faster away. It moves faster away, and then you do the very same thing, but you place it at a distance. Then you realize it moves slower, which means it simply shows you that the strength becomes weaker as you move away from the couple, as you separate the two charges. So this brings us to what we will know as this field has got a strength which is called electric field strength. Electric field strength. Spelling strength. Good. electric field strength. Now this is it. What exactly is an electric field strength? Electric field strength is nothing but now how strong is the pulling force on a what? On a point charge. How strong is the pulling force on a point charge? So which means if you are decreasing the distance, a force is going to increase. Therefore, automatically the strength is going to be stronger as well. But now a force is a what? A force is a vector quantity. Therefore, a charge is a scalar quantity. Automatically, this is going to be a vector. It's going to be a vector quantity. Suppose now you have a point charge here. Sorry, you have this charge and then you have the test charge here. Positive charge, you place it here. Then it is going to move away. Then a distance is going to be, suppose, is small letter r. Now, according to Coulomb's law, then we know that F is going to be that charge Q multiplied by the small letter point charge divided by r squared multiplied by the constant, Coulomb's constant K. So what does this mean? But we know that a force in terms of electric field is going to be F is going to be electric field strength multiplied by that charge. So if we try to equate the two, therefore if we try to equate the two, we can say therefore now K charge multiplied by test charge divided by r squared is equals to E multiplied by Q. Now you see Q is common on both sides, small q is common on both sides. Therefore, E automatically becomes K Q over R squared. Now you see this, interesting enough, why in this scenario we used a point charge. We're using a point charge because now it does not affect the electric field strength. The electric field strength is dependent on the what? On the charge. On the charge, not the point charge. And as you can see here, if the charge is bigger, electric field strength is also going to be stronger. It also depends on the what? On a distance. If you are bringing this point charge closer, and then automatically this is going to be stronger. Now these are the two equations that you need to know. E is given as K Q all over R squared. This capital letter Q, not small letter q, not a point charge but a charge. And then again another equation, E is given as F divided by Q. If you are given the point charge, then you are going to use that. Then the value of this point charge Q, the value of Q is going to be the same as the value of the electron charge. 1 times 10 to the power of negative 90 coulomb. It is the same. So if it is not given, then you know that it is like that. But it is a positive charge. Hence, you saw there, we used a positive point charge. It is a positive. Not, remember, electric charge is negative, but this one is a positive charge. Then, now you are good to go. Then application is still the same. Suppose now you have, suppose we have this charge here, then suppose it is 3 microcoulomb, and then you are placing a point charge here. Then now you need to know what is the electric field strength around that one. So therefore, and then you know, suppose the distance is 0.2 meters, I'm just saying. So therefore, electric field strength E is going to be F over Q. But then now, are you given F? No, F is not given. Therefore, you try another formula. Therefore, E is given as K Q over R squared. Can we use this one? Yes. Why? Because now Q is known, K is known, R is given. Therefore, now you just substitute. Then you know the value of K is 9 times 10 to the power of 9. Then that is given 3 micro. Simply means times 10 to the power of negative 6. Then divided by, make sure that this R is in meters. So 0,2. Then don't forget now to square this. Then now you're going to get the answer there. For now, we're not interested in an answer. But how about now you have 2 charges and 1 point charge? How about we are having this? Charge 1 is negative 3 microcoulomb. Then charge 2 is also negative, but this one is 2. Let me make it bigger. It's 2 microcoulomb. Then you place in between here, you place a positive charge here, a point charge. Now we want to know now what is going to be electric field here, strength on this one. How are these going to affect this? You must treat electric field as a vector. So now, which means draw what you call a free body diagram. Say, okay, this is a positive charge here. There is a negative charge here. Now, how is it going to affect the positive charge? It is going to pull it towards itself, isn't it? It is. Again, what do you have here? You have a negative charge, you have a positive charge. How is it going to be the effect? It is also going to pull it towards itself. But you note that the distance here is r. Suppose it's shorter r. Then suppose the distance here, as you can see, is much longer. Let us say is 2r. Which means, therefore, if the distance is longer, then the force automatically is weaker. If the distance is shorter, the force is stronger. Hence you see there I have the longer arrow than the shorter arrow. So therefore now, you must find the electric field strength due to 3 microcoulomb. Then you find the electric field strength due to 2 microcoulomb. And then now you find the resultant now, the net electric field. Therefore is going to be E3 plus E2. Now remember I said you treat this as a vector, which means if you choose this to be positive, this is going to be negative. You see? What is negative here? The direction, not the value. What is positive? The direction, not the value. So then now, which means automatically it is going to be positive E plus negative E2. This is it. Now, how about then now we have this situation? This is a one-dimensional situation. How about then now we have the two-dimensional situation? We still have this charge here. It's negative. It's a 3 microcoulomb. You have a point charge here. The distance remains the same. It is still 2r. Then instead of placing it here, we place it somewhere here now. This one. Another charge here. It is 2 microcoulomb. And then the distance remains the same. It's it's r. Now, what do you do? Still, it is going to assist you to draw a free body diagram. You draw a free body diagram just to ensure if I place it here and then I place a negative charge there, it is try by all means. It is going to affect this in such a way that it pulls it towards itself. I get it one. And then this again, it is going to do the same. It is going to pull it towards itself. Now you see what we have here. We have a tail-to-tail method. Then now we can try to complete the parallelogram. Then what do we have here? Then now this is how it is going to move instead. Instead of moving that way or this way, it is going to move that diagonal. It is going to move diagonally like this. Therefore now this is going to be the resultant. So then how do you find the resultant? You first find this one. We said it's E3 is due to 3. Remember. Then we find this one is going to be E due to 2 microcoulomb. And then now to find that one, automatically then we complete the right-angled triangle. Then simply means therefore now we are going to perform the theorem of Pythagoras. So therefore the E resultant is going to be the square root of E due to 3 squared. Sorry, it's E plus E due to 2 resultant. This is it. Same applies with if you the question was find the resultant force. We're going to do the same thing. I think this is the end of the chapter.